I've been working on change data capture, CDC for short, and Debezium for quite a few years. And usually people like it, right? So they think it's a useful tool. It helps them to address all kinds of relevant use cases for them, and they're fans. You'd like to hear that, right? But then, a while ago, I came across this blog post where somebody said, and by the way, somebody was Chris Riccomini, Kafka, change data capture, tools like Debezium, they break encapsulation. That's a bad thing. And of course, naturally, it hurt me, right? My feelings were hurt. So I didn't like that. And it made me do this talk. So I want to talk about, is there something to that? What does it mean to break encapsulation? Is it a good thing? Is it a bad thing? When is it good or when is it bad? And if it is bad, what we can do about it. So that's the idea. And I will dive into this a little bit. So, what does it mean to break encapsulation? What are those potential concerns there? And then I would like to talk about a solution to those concerns, which is data contracts. And I also will talk about a topic which I guess is close to your hearts if you use Debezium change data capture in practice, which is how you could go about managing schema changes. So that's it, what I want to do today. My name is Gunnar Morling. I work as a software engineer at a company called Decodable. We built a platform, a fully managed service for stream processing based on Apache Flink, but also then integrating with tools like Debezium, for instance. If you're using Kafka Connect, you might have come across this tool KCCuttle, which is a command line client for Kafka Connect, which I built with the KCCuttle community. And as I mentioned, I used to be the project lead for Debezium. All right, so let's get into it. And just to bring everybody on the same page, let me ask you, who has heard about Debezium? Who knows what it is? OK, that's pretty much all of you. Great. So who is using Debezium in production? That's like the brave half of you. Very good. Excellent. And just to bring everybody on the same page, I want to briefly recap what CDC is, what it does for us. In a nutshell, what change data capture is about, it's like the observer pattern for your database. What that means is, well, whenever something changes there, an insert or an update or a delete, you would like to react to that and use those events to drive all kinds of use cases, like data replication. The way this works, if this is log-based change data capture, which is what Debezium does, it taps into the transaction log, and then whenever an event is appended to the transaction log, Debezium will get this event from the transaction log, so each insert, update, delete, and send it to the outside world, typically via Apache Kafka. So most of the times Debezium users use Apache Kafka, but you also could use it with Pulsar, Google Cloud PubSub, Kinesis, with HTTP event consumers. So there's different means of using Debezium. Now, why would you like to do this? Well, as I mentioned, there's a plethora of use cases, data replication being the most widely applicable one, I would say. So, taking data from your operational database, such as Postgres or MySQL, into your data warehouse, your search index, or maybe a cache, maybe another database which you just have running on the site. You can use those change events to build audit logs. So if you just keep all those events, essentially like a Kafka topic with change events, it's kind of an audit log, right? And then you actually could use stream processing with Flink, for instance, to enrich those events with some sort of contextual metadata. So audit logging, microservices, data exchanges, all kinds of good use cases there. I happened to write I wrote a blog post recently about those use cases. You can go to this QR code. I'm a big fan of QR codes lately, so you will find many of those in my slides. So you can learn more about those use cases. All right. Now let's get a little bit closer to the problem, and this is how those change events look like, right? And I mean, if you are using Debezium, this will be familiar to you. So essentially, they correspond to the schema of a table. So in this case, it's a customers table with columns like first name and last name. And then those events, those change events, they will have a field for each of those columns in that source table. And in case this is an update event, well, we have this before and after state with the old and the new state of our row. And well, thinking about encapsulation and leaking our internal data model, it becomes a bit apparent here, right? Because, well, those fields in our change event, which we send to the outside world, they correspond to those column names in our table model. So if we were, for instance, to change them, well, we might impact our event consumers. So this is where we're getting at, right? OK. So then, let's come back to those blog posts. And again, so there's the one from Chris. There was another one from Yaroslav, talking about similar things. Change data capture is still an anti-pattern, and you still should use it. So he also acknowledges that it's useful. So definitely go and check out those blog posts, which dive into those concerns. If you don't want to read them, that's also good, because I will talk about a little bit about some of those concerns. And I'm saying potential concerns, because I also want to make the case it may not have to be a problem, but maybe it is. So first of all, and we saw it already in those change events I had on the previous slide, well, we directly expose our internal column names, table names, and also their types to the outside world, right? And well, there's the question, what happens if you change those, if you refactor our schema, but then also oftentimes our internal schemas are just not very ideal. So maybe use some sort of legacy database, it has like limitations on how long a column name could be, or maybe, you know, it's just like awkwardly named, you use weird data types, which you don't like to expose to your consumers. So that's the concern. Because your table model, essentially it becomes an API. And it's a bit of an afterthought, right? Typically, if you design your internal table model, you may not necessarily think about all those implications then if you use CDC and expose those events. So concern number one. Concern number two, well, those events are fine-grained. As we saw before, there is a correlation between our source tables in our database and the external events, or the Kafka topics those events go to, right? So we will have this one-to-one relationship. And now, sometimes this could be a problem, because if you think about your development and your design in terms of the domain-driven design, for instance, well, you will have the notion of an aggregate, for instance, right? So a higher level structure, I don't know, such as like a customer or purchase order, which might be represented in data in multiple tables in a relational database. So let's say you have a purchase order, and this will at least have a table with purchase order headers and then order lines. And typically, for your consumers, you might just want to get an event for this entire purchase order. You don't want to have those table-level events, so that would be just too fine-grained. Another concern. Then, well, I touched on this already a little bit. Well, how do we go about changing those things, right? So we might like rename our columns, we may change types, we may drop some columns, and well, if you are not careful, this then breaks our consumers, right? So if they expect a specific field with a specific name and a specific type, we go about of changing that or even removing it. Well, this might be a problem for those downstream teams, right? Again, a potential problem. And finally, there is this question, well, how much of our data do we even expose in those change events? Because, well, by default, a CDC tool like Debezium, it will give you the entire data which is in your database. So all the tables with all their columns, all their rows. And maybe that's not what you would like to expose. Maybe you have some sort of sensitive data which you would like to exclude. So maybe you just want to, you know, drop some of the columns and just expose a subset of the columns. Or maybe just expose a subset of the rows. So maybe you have, I don't know, like logically deleted rows or other data which just, you know, maybe test data which isn't meant to go in your data warehouse. So there's, again, this question about you expose all the data and maybe that's not what you want. Okay, good. I mean, that's pretty depressing, right? So it sounds like there's so many concerns and what should we do? And it's pretty terrible. CDC, it's doomed. Let's forget about it. Well, not so quick. Because I would argue, is this really a problem? Or I would question, is this really a problem? And I would say sometimes it is, sometimes it's not. It is not a problem if, for instance, we don't cross the boundaries of organizational entities. So let's say we use CDC events to update a search index, an open search, Elasticsearch, which we only use for our application, and which is managed by our same development team, which owns this particular microservice and its database, and then they also own the search index. I would argue, well, we don't really have a problem here because, well, if they change the schema in their database, then they explicitly want to also change the structure in the search index, or maybe a cache, which they have for quick read access. So they want this close relationship. So in that case, I would argue, well, it's not a problem because we don't cross the boundaries of like teams, you know, and like organizational units in a larger company. So it's fine. But then, well, let's say, you know, those events are actually consumed by a team which we maybe, I know, we don't talk to them. We talk to them like once per year if we see them at a Christmas party. Otherwise, we don't talk with those guys and they consume our change event feed. Maybe we don't even know them at all, right? So we might also publish a change event feed and we don't know our consumers. Well, in that case, yes, we may have some problems, right? Because then if we go and just change our schema, for instance, well, then we would break them and we wouldn't even have told them. So in that case, it would be a problem. All right, so of course, I mean, I guess there's some hope because, yes, we can acknowledge that there are those questions, but there's also something which we can do about it. And this is, well, this notion of data contracts. So let's dive into this a little bit. And I want to read it out to you what it means. Well, a data contract, it's a document that defines the structure, the format, semantics, quality, and terms of use for exchanging data between a data provider and data consumers. So essentially, it's a formal description of our data. And if I say contract, I mean, it's not something, which you sign with the blood of your firstborn and it's like legally binding or whatever, but it's a formal specification, right? And there you describe, okay, what is the schema, for instance, of my data? What are the names? What are the types? What are the semantics? So like if I have numeric value, what are the units of measurements? If this is like a timestamp, is this like in milliseconds, microseconds? So it's about the semantics. It could contain, things like SLAs, service level agreements. It could give hints at like examples, data quality, all kinds of things which consumers need to interact meaningfully with such a data stream. So that's the idea. We want to put this into some sort of formal specification, and there could be different means of doing that. And then our consumers can go, let's say, to some repository where those contracts are managed, fetch them, and then have some stricter understanding of what those change event streams look like. Now, in terms of how, or let me say, essentially, it's about documenting the intent, right? So instead of just like setting up this CDC tool as sort of an afterthought and then hope for the best, the notion here as well, you want to publish consciously designed, data contracts, streams with consciously designed semantics and schemas and so on, and publish this as some sort of a data product, right? So that's the idea. And very important when doing that as well, you would like to have those data contracts and the means of creating them to be owned by the team which manages that source application, which publishes this, right? So it's sort of a data product in a sense. Now, how to do this? And I realize this is very small, doesn't really matter because it's just like tons of YAML. Well, you could put this into a wiki, for instance, but you also could use this specification or YAML schema from datacontract.com where they, give some means of doing that. So there's different ways, right? So it's just something you need to decide. So how do we document our data contracts in our organization, our context, right? And then, of course, like all the event publishers, consumers, they should be on board with that. Now, I would like to dive into implementing data contracts, in particular the schema part, right? So I don't care for the purposes of this talk about things like SLAs or examples or whatever. I would like to talk about how we can implement data contracts from a schema perspective. And there's two things I want to mention. There's the outbox pattern and there's stream processing. So let's dive into the first one, outbox pattern. So who has heard about the outbox pattern? That's like, okay, maybe 1/3. Okay, not as widely known yet. So the idea there is, well, instead of publishing change events for our actual business table model, we would like to publish a specific event stream. And the idea is, well, you're writing an application which goes, in this case, to this Postgres database and issues its transactions. It updates the internal table model. So let's say we are in an e-commerce situation. We will issue rights to our purchase order table, to our order lines table. And then as part of that transaction, we also insert an event to a specific outbox table. And the events in this outbox table, they are now the events which are sent to our outside event consumers. So now you would use a CDC tool like Debezium, to only react to changes in this outbox table. And by the way, when I say changes, well, this actually only ever is inserts because, well, this outbox table, again, it's like an append-only immutable event log, right? So you don't want to alter events after they have been issued. So all those events are inserted into this outbox table. You use then Debezium to capture the inserts into this table, and you send only those outbox events to your event consumers. And now this solves this problem which we have because, well, now we have the separation between our internal table model with our internal tables and then the data schema which we use in this outbox event, right? So in this case, it's it's a JSON structure. It could also be like, I don't know, protobuf or whatever. But the important thing is this is independent from our internal table model. So if we were to do changes to the internal table model, then we could consciously decide, do we also want to modify those message schemas which we use in the outbox table, or maybe not? So maybe we want to shield our external consumers from those internal data changes. And very importantly, the writes into our table, into our actual business tables, and into this outbox table, they happen as part of one transaction. Right? So this means either this transaction gets committed, which means we also get to issue this insert into the outbox table, Debezium will capture it and send it to Kafka, or our transaction gets rolled back, which means we don't do any changes, right? No changes to our model, and also no outbox message gets sent. So this happens atomically. So that's the outbox pattern. I would say it's an interesting, relatively simple means of avoiding all those concerns which we had, at the price that our application needs to support that, right? So our application needs to do those inserts into this outbox table, and it needs to do that whenever we modify our data, right? And again, it could be a problem or not. So maybe it's an application which we don't want to touch. It's some sort of legacy application. I mean, I've worked in situations where we didn't even have the source code for running applications. So, in that situation, it might be not desirable. But if you can modify the code of your application, and this is fine for you, and you also you're sure you will never forget to send this sort of outbox event, I would say it's a very legitimate solution, and it's widely used in practice. All right, so let's talk a little bit about an alternative, which comes with its own trade-offs, and this would be stream processing. And I suppose by now most of you have heard about tools like Apache Flink or Spark structured streaming or whatever. Different options there exist. But with those tools like Flink, we can actually take those raw change event streams with our table-level events and process them and massage the data on those streams before we send them to the outside world. So that's the idea for using stream processing here. Now, Flink, it's a huge topic by itself. So there's many talks you could have just on the different concepts and ideas of Flink. So there's different APIs which exist with different levels of flexibility, different levels of abstractness. And at the top of those API stack, there's what's called Flink SQL. So a relational SQL-based API for implementing stream processing jobs. And as it turns out, this is actually a very powerful tool for implementing those streaming data contracts. So let's dive into this one a little bit. Now, to give an example again, so let's say we have this sort of table there with our customers. And now we would like to create a specifically designed schema which we would then expose to our event consumers. So the original internal schema on the left-hand side, the public user-facing or consumer-facing schema on the right-hand side. And you see there's some differences there, right? So for instance, there's like difference in terms of names. So it's F name and L name. So there's weird short legacy names in the source schema. And we would like to have like nicer names, first name and last name in the public messages which we send out. There's differences in terms of types. So if you look at the status, for instance, that's like an int code in our internal schema. Maybe we would like to have like enums, proper labels in our public events. So differences in types. Also the same goes for the registration date, which also, by the way, gets renamed. So, we want to change this from a timestamp, into some ISO formatted string, for instance. And also it's a subset of our data, right? So not all the columns in our source table are part of that public schema. So how could we implement this with Flink and Flink SQL? This is what we can see at the bottom there. So we would have our database. I'm a big fan of Postgres, so that's what I've drawn here, but it would again work for other databases, of course, as well. We would use then change data capture as a tool to ingest those change events. And now, if we want to integrate Debezium with Flink, there's, roughly speaking, two different means of doing that. And one is, which we see here, this is using what's called Flink CDC. So this is a native integration of CDC and Debezium into Flink. So it's running as a source connector directly within Flink, using what's called the Debezium embedded engine. And now this means you don't have to go through Kafka to get your events from Debezium into Flink. Instead, it would be directly a connector, a source connector running within the Flink process. So it's a bit easier to operate typically. But then again, you also lose some sort of optionality with that, right? Because if you have your change events on a Kafka stream, well, you could like replay them, set up new stream processing jobs down the road. So there's different ways for using Flink, using Debezium with Flink. Both have pros and cons. Here I'm using Flink CDC. So then we would have our stream processing job, our SQL, which takes that data and those messages which look like that on the left-hand side and converts them into the format on the right-hand side. We will see how that goes. And then we could use all kinds of Flink sync connectors. In this case here, I'm using the Kafka sync to put out the data onto some Kafka topic. So to set this up, we would define two tables in Flink. And our source table, it has this source schema which we saw. And then at the bottom, we see this metadata there, which defines how is this table sourced. So this says, OK, this is using the Postgres CDC connector with all the database details, credentials, and so on. So we know which table this is coming from, username, password, and so on. And now this table, somewhat unintuitively, this represents an incrementally updated view on our data. So whenever there's now a change in our source table, in our source database, Debezium will capture that. And this table here in Flink, this will always represent the latest state of that data. So that's our source table. Then our sync table, same thing pretty much. Our schema now is this public user-facing schema, which we would like to publish to Kafka. So with, for instance, you see already it has like different field names for fname and first name, for instance. And now in this case, then this uses the Kafka upsert connector going to a specific Kafka cluster to write the data there. And of course, the question is, how do we get the data now from our source table into our sync table? And for that, well, again, we can use SQL, and we define a very simple, I would say, stream processing job. And the way this works is always we have a select, which takes, which selects our data from, in this case, from one table, but we also could like join multiple tables, for instance. And then we do this insert into to say into which table this should go. And we would submit this as a job onto our Flink cluster, and then this would incrementally, continuously run. And whenever something in the source table changes, it would select this data and then put the affected records into that sync table. And now this is where we do those transformations, right? So here, then, for instance, we do this dance with our enum, right? So we convert the numeric status code into those nicely readable labels, or we change this timestamp into a specifically formatted timestamp string. So, this is this processing logic there. And I would say, it's not too complex to implement that. And now we have achieved those advantages, right? So we have decoupled our event source from our event consumers. Of course, there's more which we could do. So we could do things like filtering our data. So let's say we want to exclude all the customers which have this test account flag set, right? So we only include those which are not a test account. We could do this. We could have derived data fields. So maybe we want to have a name with the full customer name. So we just could concat some data. We also could have what you could call consumer-specific contracts. So you could have multiple versions, multiple flavors of that data, which are geared towards specific consumers. So a common example there is if you do backfilling with Debezium, like re-snapshotting, parts of your data because, I don't know, maybe that's like a new table, or you would just like to recapture, re-snapshot some amount of data. Then maybe some of your consumers would like to have those re-snapshot events, and some other consumers don't. So you could have different consumer-specific flavors of that, which then, different consumers could subscribe to. And of course, there's more things we could or we can do going beyond just, those basic stateless transformations. We also can do stateful transformations. And this is what we see here. And this addresses this concern which we had about the granularity of our events. So the example here would be, we have like a customers table, and now let's say instead of a single phone number. In our table model, actually, we say each customer can have multiple phone numbers, and one of them could be preferred, right? So the way you would typically model this in a relational database is pretty much like you see it here on the left-hand side. So you would have two tables, foreign key relationship, 1 to n. Multiple phone number records could point to the same customer record. And now in our change events, we don't want to have change events for customers and then separate change events for phone numbers, right? So for our consumers, this would be relatively tricky to handle. What we rather would have is this, what we see here on the right-hand side. So something like an array of our data, right? So essentially this kind of nested data structure. So here we have, a change event for one customer with all that data, and now the phone numbers, they are embedded into this as an array. And now whenever anything in the customer changes, or if the phone number changes, they would get this event, and they would have the entire view onto one customer. How can we go and build this? Well, it turns out as of Flink 120, it's relatively simple because there is this array egg function, which essentially takes several elements, in this case, on the many side of a 1 to n join, and emits them as an array. So it exactly does what we want. It takes the events from the phone number side of our join and emits them as an array. So this is new in Flink 1.20, so you just can use this function there. If you are on an older Flink version, well, I recorded the video a while ago where I showed you how to implement this sort of UDF. So you can go to our YouTube channel, Decodable YouTube channel, where you can see how to implement this sort of UDF like array egg in this example, and find out how to do it. So it's not too involved. Takes about 10 minutes to watch that. All right. What else can we do? Well, that's also a classic one, in particular for those of you who use Debezium with Postgres. So in Postgres, you have this notion of toast columns. So essentially, it's large columns which have a large binary or large character payload, larger than 2 kilobytes or something like that. And now, just by means of how CDC is implemented in Postgres, if you have an update to a record and you have one of those toast columns and the value of this toast column doesn't change, then Postgres will not give us the value of this unchanged column. So instead, we won't get that value. And so our events are not fully, they don't fully describe our data, right? So they wouldn't have all the fields. They would lack those unchanged toast values. So in case of Debezium, the way this is exposed, you would get then this marker value, this special magic value, Debezium unavailable value. So this tells you, okay, this is a toast column, its value didn't change, so we cannot give you the previous value. And this is kind of not really ideal because, well, if you have consumers, so what do we do now with those markers? Instead, we would like to have change events which always contain the full view onto our data. And again, with just a bit of stream processing, this is something which we can implement. Now, this is not SQL, obviously, but it's the data stream API. But the implementation is relatively simple. So all we need to do is implement a little mapping function. And there we would keep a state store. And the idea is because from the insert for those records, we will get those toast columns. So if we see the very first change event for a particular record, we will see all those values. Now we can put them into some state store, and then if we process further change events, we can look what type are they. So if this is like a create event, so then we would put the event and this particular value into the state store. And now if this is an update event, well, we would actually go to our state store and then replace this marker value with the value which we had in the state store before. So few lines of Java code in that case to then get rid of that notion of toast columns, and our consumers then don't have to deal with that, right? Because if we are consuming those change events in our data warehouse or whatever, we want to be abstracted from all those things, right? I would say that's like a prime example for, yes, CDC does break encapsulation in that situation because, well, this is such a specific implementation detail, we don't want our consumers to have to understand about it, right? And with a bit of stream processing, we can handle that. And I hope we will have that in the Decodable platform out of the box very soon. Okay, So then let me talk a little bit about schema changes, because I mean, that's always a hot topic. And the key thing there is, and this goes back to this notion of having a data product and having this team which owns a source application, they also should be the ones which publish this change event stream, and they should be the ones who do changes to that schema of that change event stream. And if you have been using the Confluent schema registry, there you have this notion of forward compatible changes and backward compatible changes. And now in our case, as our producing application should own the schema and should own schema changes, we should do what's called forward compatible changes, which essentially means if there's a consumer which has a previous version of our data schema, they can still ingest those schemas, those messages which have a newer schema without failing. So let's say we have like this message on the right-hand side, with first name, middle name, last name. That's the first version of our schema. So we send out those events, our consumers process them just nicely. And then we want to do a change. So we want to drop that middle name column. And if you look at the version 1 of that schema, that is an optional column. So it was not null, it was like, optional. And we also want to add like a title column for the sake of the example. And no, those two changes, they are forward compatible because, we can drop an optional column, right? So if I have a consumer which still has the first version of that contract, if they receive a message without that optional value, they are already prepared for that, right? So they will just be fine. And similarly, if we add fields to that message, which this consumer of the first version, or this consumer which has this first version of the schema doesn't know yet, well, they probably will just ignore it, but they won't fail. So that's a perfectly fine change to do. Whereas on the left-hand side, this is not forward compatible. So what happens there is we actually drop a mandatory, a non-nullable field. And now this will break any consumers which still expect that field, right? So that's not something which we should do. We should always do forward compatible changes. How could we go and implement it? So let's say, let's look at an example again. So here in this case, I want to go and change my schema, my internal schema, from version 1 to schema 2. And now I do a simple rename. I mean, that happens quite often, right? So we want to rename fname to first name in our internal schema. Now for our customer or user-facing contract, this should be like an opaque detail because there we had already like first name and last name like properly defined, right? So we just need to make sure if we do this change in our internal table model that we don't break anything. So how could we do this? Well, in terms of Flink and Flink SQL, what we would do is we would first of all stop this previously running job, which I showed before, like this select into. So we would stop that, and we would stop it with what's called a save point. So this keeps track of how far we have processed that source table. So we shut it down and essentially remember how far we have consumed those change events. Then we go to our source table and do that schema change. So we do that rename from fname to first name. And it's very important to do those steps in that order. Because then what happens next is, we want to modify how we expose or how we ingest that data into Flink. So there, we cannot just change that because we could still ingest events which have like the old name. So instead, we add this column into our source table in Flink. So we would have both of them, fname and first name. And I got to save where I want to store that save point. And what you see here is, this is why it's so important that this team which manages the source database and the source application also owns that Flink job which publishes those change events. Because if you don't do those steps in the correct order, we might end up with incomplete data, right? So this is a process which just requires close coordination between those steps, and that's why it should be owned by one single team. And the last thing missing there is where we need to update our processing job, which takes the data from the source table to the sync table. And in that case, we will just use this coalesce function to either propagate the fname, if this is like a message from before the schema change which we process, or the first name if this is a message from after the schema change. And then we would of course like emit it using the first name as a name in both cases. So our consumers, they won't be impacted by that. So right now, we were able to modify and refactor our internal table schema without making any of that visible to our event consumers. All right. Let's wrap it up. Looks pretty good time-wise. I guess there will be some time for questions. So, just to dive on or touch on some of the takeaways. Well, I mean, most of you, pretty much like 90%, use Debezium, so I don't have to make a strong case for that. But it gives you real-time change event feeds for all kinds of databases. Very useful tool with many use cases, as we've seen. Adding Flink and stream processing into the mix, this helps us to address some of those concerns which you may or may not have around using CDC, right? So as we saw, well, we encapsulate now our internal data models, right? So because we have a consciously designed or defined version of a message schema which we expose to event consumers, which is independent from our internal schema. So that concern is addressed. And we spoke about compatibility, right? So in the schema changes example, renaming things, and I could do other kinds of schema changes as well. So we can do schema changes and still make sure that those events which we are sent out, that they are still compatible for our event consumers. And also, well, we saw it with those filter examples where it was like excluding some data. We also are, addressing that concern about like, do we expose like too much data? Do we expose sensitive data? So we can put those means of filtering into place. So do we have a problem or do we not have a problem? Well, I think I could make the case sometimes we do, sometimes we don't. But if we do, then we know how to do it, right? So I feel like those tools, in particular Flink and Flink SQL, they help us with that. Before I'm wrapping up, I want to send you home with this interesting chart, which unfortunately I didn't come up with myself. I found it in a book, but I found it very useful. So if you think about those tools like Debezium and Flink and the events which we get with them, if you look at the value of events, well, individual events, they have a very high value as they are new and fresh, right? So if you look at change events for a particular purchase order, the value of those events is very high early on. I don't know, you want to send them to your fulfillment system, this should happen as quickly as possible, right? Or maybe you want to use those events to, issue some payment, this should happen as quickly as possible. The value of those individual events then goes down over time. So if you look at change events for a particular purchase order or for a particular customer from like last year, that's not too interesting, right? So all those purchase orders and all those customer data, this has been processed a long time ago. So the value of individual events goes down, but then the value of aggregated events, that goes up, right? So if you look at all the change events from all our customers, all our purchase orders, we might be able to gain interesting insights into that data, right? You could do things like, customers who purchased that item, they also purchased that item, things like that, right? So the aggregated value goes up, and those tools like Debezium and Flink, they help us with either side of those curves. If you want to learn more about this, I wrote a blog post. Pretty much this talk is the oral version of that blog post, so you can read it up. There's also an example in the Decodable examples repo, which shows you how to implement those things using Flink SQL, Flink CDC. So definitely check that out. And I have to do a short commercial break, so there's other people from Decodable who are having talks here. So my good colleague and friend Robin is going to do a talk about all the troubles you may have or may not have with jars. Sharon is doing a talk about the notion of time, like right in the next slot after this talk. And Hans-Peter Grase is talking about user-defined functions, something like those array egg functions. So you can go to his talk to learn more about doing that. That's all I had for you today. If you would like to stay in touch, send me an email, follow me on Twitter, go to my blog. I don't know where this QR code is taking you, to be honest. Go and find it out. I hope it's not so nasty. And I think we have like 5 minutes for questions. Thank you so much.